If you stack the Eiffel Tower on top of itself 4 times, you get a pretty good sense of its massive sweeping scale. Now, I want you to imagine generating that exact sheer volume, but in raw digital information every single day.
It's pretty hard to wrap your head around, honestly.
It really is. Welcome to the Deep Dive. Today we are looking at a staggering reality, which is that the modern world produces 2.5 quintillion bytes of data daily. And we are going to explore exactly what happens to, all of it.
Yeah, it is just a phenomenal amount of material, and we are well past the point of data just being a byproduct of our digital habits.
Right, it's a main event now.
Exactly. We are firmly in the middle of Industry 4.0, that cyber-physical era where algorithms, the Internet of Things, and physical manufacturing, they just completely blur together.
The blurring of the physical, the digital, and even the biological worlds.
Yeah, precisely. But the actual hardware, the robots and the sensors, that isn't the real story here.
Oh.
No, the driver of this entire era is that massive volume of data. It's essentially acting as its bloodline.
Okay, let's unpack this. Because to understand how that bloodline actually functions, we have to look at the raw scale first.
Right.
Processing power, internet speeds, and storage capacity, they've been doubling every 2 years, while costs just absolutely plummet.
Yeah, the Moore's Law effect, basically.
Exactly. So by the year 2020, global data had reached about 64 zettabytes, and projections show us hitting 180 zettabytes by 2025.
Which is just a massive, mind-boggling number.
It is. Just to visualize a single internet minute from recent years, like in just 60 seconds.
Let's hear it.
400,000 hours of Netflix are streamed.
Wow.
41 million WhatsApp messages are sent, and 500 hours of YouTube video are uploaded in 60 seconds.
And it's just nonstop.
That is 180 zettabytes of a global bloodline, allowing machines to communicate and update AI models totally without us.
Which sounds incredibly efficient, until you realize what the vast majority of that information actually looks like.
What do you mean?
Well, you mentioned 180 zettabytes, but what often gets overlooked is that roughly 80% of all global data is what we call dark data.
Wait, dark data, meaning like it's encrypted or hidden by firewalls?
No, not exactly.
Because if I don't know, hoarding digital trash on servers somewhere, like why is this dark data actually valuable to you, the listener, or to a business trying to stay competitive?
What's fascinating here is that dark data isn't hidden by encryption at all. It's just completely unstructured.
Unstructured, yeah.
Yeah. In the industry, we often talk about the 5 V's of data: volume, velocity, variety, veracity, and value.
Right, the 5 V's.
And when people hear big data, they immediately focus on volume, like the massive size of it.
Sure, but this sounds impressive.
Exactly. But the real magic, the actual competitive advantage, lies entirely in variety.
Meaning it's not neatly formatted in a clean, organized spreadsheet somewhere?
Precisely. Unstructured dark data is just a chaotic mess.
Like what?
Well, it's text from a furious customer review, or the pixel data in a blurry security video.
Oh, I see.
It's the audio waveform of a machine running on a factory floor, or raw time series data from a temperature sensor. Traditional databases, they just can't read that. It literally looks like trash to them.
But it's not trash.
No, because hidden inside that massive diversity are micro patterns.
Micro patterns. Okay, give me an example of how a business actually pulls a pattern out of chaotic trash.
Okay, let's look at a factory floor. A traditional setup might have a dedicated temperature sensor on a massive motor.
Okay, makes sense.
When the motor gets too hot, the sensor trips, an alarm sounds, and a human comes over to fix it.
Right, that's traditional structured data. It's simple.
Exactly. But what if you use an AI algorithm to analyze the ambient background noise captured by the factory's standard security cameras?
The unstructured dark data.
Yes. The AI can identify the specific high-frequency audio micropattern of a motor bearing starting to grind.
Oh.
Yeah, it detects the failure from the sound waves weeks before the friction ever generates enough heat to trigger that traditional temperature sensor.
So we're basically sitting on an invisible goldmine of insights. We just didn't have the algorithms to hear the grinding, so to speak.
Yeah, that's a great way to put it.
But, I mean, a human manager isn't sitting there listening to thousands of hours of ambient factory noise hoping to catch a squeak.
Definitely not.
So how does a company systematically turn that chaotic audio file into an actual business decision?
Well, they follow a very specific progression chain. Data becomes information, which becomes knowledge, which synthesizes into insight, and finally it arrives at wisdom.
Data to wisdom. Got it.
And to get to wisdom, businesses utilize 3 distinct levels of analytics.
I imagine the first level is just figuring out what is currently on fire.
Basically, yeah. The first level is descriptive analytics, which simply asks, what happened?
The motor failed.
Exactly. The second level is predictive analytics, which asks, what will happen?
So the algorithm hears the grinding and predicts the motor will fail in 3 weeks.
You got it. But the ultimate goal, the wisdom phase we talked about, is the third level, which is prescriptive analytics.
Prescriptive, like a doctor giving a prescription.
Exactly. This asks, what should we do about it?
Here's where it gets really interesting. Let me see if I can make this prescriptive analytics idea concrete for a second.
Sure, go for it.
Imagine the smart sensors in your own car. Descriptive is the check engine light coming on. Something is broken.
Right.
Predictive is the car analyzing its own vibration data and realizing the alternator is going to die next Tuesday.
Yep.
Prescriptive is the car taking that knowledge, checking your personal calendar, automatically ordering the replacement alternator online, and scheduling a mechanic for your next free afternoon. All without you lifting a single finger.
That captures the mechanism perfectly. Now, I want you to scale that mechanism up to an entire global supply chain.
Okay, that's huge.
Take a company like Kiva Systems. They operate self-charging, Wi-Fi-equipped robots in massive warehouses.
Oh yeah, those little orange robots that zip around.
Exactly. These robots don't just follow a static track. They are constantly analyzing unstructured data.
Like what kind of data?
The weight of their load, the friction on their wheels, the real-time location of every other robot on the floor. And they use prescriptive analytics to autonomously alter their routes to prevent traffic jams before they even occur.
Which completely eliminates the concept of unplanned downtime. If everything is predicted and prescribed, nothing breaks unexpectedly.
And this is where the underlying technology becomes just so crucial.
Yeah.
Because if you try to run traditional algorithms on a normal-sized data set to predict these failures, you might hit an accuracy rate of, say, 75 to 85%.
Which is helpful, but a 15% error rate in a multi-million-dollar warehouse is still a massive financial loss.
Exactly. However, when you introduce massive zettabyte-level data sets and unleash deep learning and neural networks, everything changes.
Because neural networks process information differently, right?
Yeah, they work in interconnected layers, much like a human brain, so they can cross-reference millions of seemingly unrelated micro-patterns.
So instead of just looking at the robot's wheel friction, it's comparing the wheel friction against, like, the humidity in the warehouse, the battery degradation curve, and the weight distribution of the package.
Yes, and by layering those micro-patterns, the accuracy jumps from 85% to 95 or even 97%.
That's a massive jump.
It is. Suddenly, you aren't just reacting to data silos anymore. You have an integrated management system. Quality, safety, environmental, and energy data are all talking to each other.
Oh.
You optimize inventory on the fly, which drastically reduces operational costs.
But let's ground this in physical reality for a second.
Okay.
Because if I try to open a single spreadsheet with a million rows, my laptop fan sounds like a jet engine preparing for takeoff.
Oh, absolutely.
So if an entire global company is trying to crunch petabytes of unstructured video, audio, and sensor data simultaneously to hit that 97% accuracy, traditional computers simply cannot handle that. It physically breaks the processor.
It really does.
How did the tech world actually solve the physical bottleneck of 180 zettabytes?
Well, they had to completely abandon traditional computing architecture. The old way of processing data had massive fundamental flaws when introduced to this kind of scale.
Like what?
The biggest issue is known as the critical path problem.
Meaning what exactly?
In a traditional setup, if you have a massive computation, you divide the job among several machines.
Right, parallel processing.
Exactly. But the final output relies on every single machine finishing its part. If you give one machine a slightly more complex piece of the data, or if one machine has a slightly older processor, it lags behind.
Oh,
And then the entire multi-million-dollar operation grinds to a halt, waiting for that one single slow machine to finish its critical path.
You're only as fast as your slowest worker.
Precisely.
And I imagine if that slow worker's machine literally catches on fire, the whole system crashes.
That's the reliability failure. So to solve the critical path and the reliability problems, the tech industry developed distributed computing frameworks.
Which ones?
The giants in this space are the Apache Hadoop ecosystem and Apache Spark. They are built on underlying frameworks originally pioneered by Google.
Okay.
The core genius of Hadoop comes down to a technique called MapReduce, and its reliance on something called data locality.
Data locality, meaning instead of bringing the data to the computer, you're bringing the computer to the data.
In a sense, yes. Traditionally, you have a massive central processor, and you transfer heavy, dense data across a network to that processor.
Right.
But transferring petabytes of video files clogs the network, and it literally takes days. MapReduce flips that entirely. It sends the processing logic, the actual algorithm, out to the individual storage nodes where the data already lives.
Okay, let me visualize this. Imagine you're trying to cook a massive, complicated feast.
I like feasts.
Right. So the traditional computing way is moving a literal mountain of raw ingredients from farms all over the world to one master chef in a single central kitchen.
Which should be a nightmare.
Exactly. It takes forever, the roads get congested, and the chef is totally overwhelmed.
Right.
MapReduce essentially takes the recipe, the algorithm, and copies it 1,000 times, sending 1,000 sous chefs directly out into the fields to chop and prepare the ingredients right where they grew simultaneously.
If we connect this to the bigger picture, that approach completely eradicates the critical path problem.
Because everyone works independently.
Yes, every sous chef is only responsible for their own small plot of data. They process it locally, in parallel, and then just send the tiny finished result back to the center.
That is brilliant.
But the brilliance of Hadoop doesn't stop there. The other half of the equation is a concept called sharding.
Sharding, like breaking a glass into shards.
Similar concept, but for data distribution. Instead of keeping all your unstructured data on one massive hard drive, sharding breaks the data into blocks and distributes it across hundreds of smaller, cheaper standard machines.
Okay, so spreading it out.
Right. But crucially, it creates multiple overlapping copies of those shards.
So back to the farm analogy. If one of those sous chefs gets sick in the field or their tractor breaks down, the meal isn't ruined.
Exactly, because of the overlapping copies. Sharding means every vegetable, every piece of data has 2 or 3 sous chefs assigned to it in the background.
Oh, redundancy.
Yes. If one node suddenly loses power or crashes, the central system instantly redirects the algorithm to the backup shard on a different machine. The user never even sees a blip.
That's incredible.
It creates incredible fault tolerance. You don't need to buy a $50 million supercomputer anymore. You can build a highly scalable, robust infrastructure out of relatively cheap, off-the-shelf servers because the software itself handles the failures.
Okay, so the physical bottleneck is solved. We aren't melting servers, and we have the software to distribute the workload.
Yep.
But the landscape is constantly shifting. The infrastructure to handle all this is physically moving, causing a massive reliance on cloud computing. Like, we are moving away from companies owning massive server rooms in their basements.
Oh, absolutely. The sheer velocity of data growth makes owning your own servers a liability now.
Too expensive to upgrade.
Yeah, you constantly have to buy new hardware just to keep up. Cloud computing offers elastic scalability. You rent the processing power you need exactly when you need it.
Right.
However, the modern reality is the rise of the hybrid cloud.
Because throwing your company's most sensitive data onto a public server shared by millions of other people is a massive security risk.
And often completely illegal depending on the industry you're in.
Like healthcare.
Exactly. A hybrid cloud integrates public clouds, which give you that massive agility and scale for heavy algorithm crunching, with private on-premise clouds.
Oh, I see.
If you are in healthcare or finance, strict regulations require your sensitive patient or financial data to remain behind a firewall on a private cloud.
Right, that makes sense.
The hybrid model lets an organization securely store the sensitive data locally while pushing the non-sensitive, heavy computational workloads out to the public cloud.
And within those clouds, the physical way we organize the data is splitting into 2 very different philosophies. The terminology used is data warehouses versus data lakes.
Yes. The distinction between the two is critical for how a business actually extracts that wisdom we talked about earlier.
Let's use an analogy here. Think of a data warehouse, like a massive, highly organized grocery store.
Okay.
It stores maybe terabytes of cleansed, structured data. Every piece of information has been processed and placed in a specific aisle with a clear label.
Very orderly.
Right. It's designed specifically for business intelligence reporting. It's neat, it's organized, and it's meant for a human being to easily walk down